Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
Hey, look, we made it.
Hello, everybody.
Yeah.
How are you all doing?
I should check that the audio is correct. It just occurred to me, and I think it is.
It is?
I hope so. I hope everybody
so?
can hear us. This is a bit touch and go here. We're not usually this scattered, you know. We're usually more professional.
A little more professional. Let's not kid ourselves, everybody.
Yeah, I mean, like moderate levels of
like
professionalism.
moderate levels of professionalism right now.
That's right, exactly. Except today you got pulled aside for other work things. So it's like professional in a different way because you're doing, you know, our job that we're supposed to be doing that we sometimes try to do.
that we absolutely do.
Well, we do.
We absolutely
that's
do.
True. We do.
I
shouldn't slander ourselves and say we don't do our job.
Yeah.
That all we do is just live stream and just, you know.
I wish.
Just play on the internet all day. That's all we do.
Just love to be a live streamer all day, every day.
That would be
live
fun.
Streaming. That would be fun.
That would be kind of fun. I think I would like that if we had if this was just our job and all we had to do was just live stream. You know, it always makes me think that if you have like live streamers or like, I don't know, podcasters or whatever, you know, videos are all different because it takes a lot of time to make a video. Yeah. But you have these people that do these shows. It always seems like they just pop on, talk for a couple hours, and then they're done. And it's like, the reality, of course, as we know, because we make webinars and we make videos, all this content is like it's like 5,000 to 1, you know, at the least, like
work too.
Yeah, exactly. So it's like if you do an hour or 2 hours or whatever, it's a huge amount of effort behind the scenes. It just looks like you're just, hey, I'm just live streaming, just talking, and it's like it's actually a lot of effort.
It is a lot of effort.
It's a lot of work.
I would also say it's a lot of like upfront work. At a certain point, you can get things to go like smoothly, but no, it is a lot of work.
Yeah, it's true. Well, anyway, welcome everybody. I hope that's a good intro there for you. I'm actually shocked we made it, but we did. We're here for another episode, and I guess let's get right to it.
Yeah.
Here. So TT is back. Good to see you.
Hey, TT.
Says, hi, how to significantly use Bode plots, like how to interpret, discuss both plots with regards to supercapacitors. Don't. Nobody cares. Okay, let's see. I probably have some data that might...
like significantly use a Bode plot. That's an interesting...
I prefer to insignificantly use my data, you know? Like, I'll use it, but I'm not going to be a spaz about it, you know? Like, that reminds me, it's like a Jim Gaffigan joke. He's talking about his wife had a procedure, and he's like, we were in the intensive care unit, but you know, it's like that supposes that there's like a not intensive care unit. Like, well, we care, but we're not going to be a spaz about it. I love it. Let's see. Do I have any data that even looks like? You said that the tricky thing about supercapacitors is that they often don't have what I might call like interesting looking data. Because it's a capacitor, like it's just a straight line. You know what I mean?
Yeah.
Let me.
If you have a pure capacitor, and then like, okay, if you look at the Bode plot, can you analyze the Bode plot so that you could learn some very interesting things?
Yeah.
I mean, so I think this also while you prepare some stuff, I think this is also a very important thing on like from like a science perspective. Like when I'm doing experiments. Maybe I have to weigh out, you know, my sample, and it's like, all right, I got like the mass of my sample. How can I really use this mass of my sample to really make some like interpret this, you know, what this mass means? What does 5 grams really mean? It's like sometimes you don't have to overcomplicate certain things just because like you have this Bode plot, it looks like it has a lot of stuff, but maybe it just tells you one thing that's very important, and then you just take that one thing and you just go with it. You don't have to look deeply into the Bode plot.
That's actually a really good point, and it leads into probably one of the main things that I'm going to say about advice about this, which is actually just exactly kind of what you just said, is that like, what am I getting out of the Bode plot? Okay, well, maybe one thing and that's enough. Like, you don't have to get all the things. So to that point, this is the data that I have that might be something. It's not really. There's like a semicircle here and there's a bit of a diffusional tail, but let's pretend that this was like, I'm going to unorthonormal. Let's pretend this was something like this. This might look kind of, I'm manipulating it on purpose to cheat. So like maybe a supercapacitor would look something like this if the axes were actually properly oriented, which they're not. I'm cheating. Yeah, I said like a vertical line of some kind or whatever. But I suppose let me talk through some of my thoughts to your question. The first is that your question almost highlights a different point, which is that it's why having both plots visible is actually important, because the Nyquist plot is really nice for the patterns and the recognition of, oh, this semicircle, that's charge transfer process. This line is capacitance or diffusion, but there's no frequency axis. And so that's why the Bode plot's helpful. You have a frequency axis. You can also see how the impedance changes, the red line. So having both visible is a very nice thing to be able to have. Okay. But to Alex's point, what's like one thing you can do? Now, this is my opinion. It's relatively educated and well-founded opinion, but still it's my opinion, and someone else could certainly have a different opinion. My opinion on the Bode plot is that the phase angle is the more important one. The blue on this right here, what you're looking at, right? This blue trace is the one that matters. It's the one that I tend to draw the most conclusions from and care the most about. And the reason is that a couple of reasons. So first is that with the red line here, the impedance magnitude, that half of the Bode plot, often you don't see a lot of useful information. Now, the number of times that the red on the Bode plot, that the impedance magnitude sort of flattens or plateaus, can also kind of be an indication of the number of like charge transfer processes that are occurring. So that's one way to interpret it. So you can kind of look at this as like there's flat here, kinda, and then it ticks up and then it kind of flattens out a little, or maybe it's creeping. See, this is what I'm talking through is actually an illustration of why I don't like the impedance magnitude trace that much. It's like, well, what am I looking at? There's kind of a bit of a change in slope like 2 times maybe, and that's about it. But it's just mostly that the impedance magnitude is increasing as the frequency drops. That's almost always the case unless you have an inductive element. So there isn't, it's hard, and it's logarithmic too. So in other words, changes in the Y scale are harder to observe because it's logarithmically plotted. So I find the impedance magnitude to be a little bit of one that I ignore most of the time, to be perfectly honest. The phase angle, on the other hand, is not logarithmic. It usually goes between 0 and minus 90 degrees. There's a lot of conclusions you can draw from it very quickly. So one of them, for example, is that wherever at frequencies on the x-axis here, that the phase angle is close to 0, it is behaving most like a resistor. As well, wherever the phase angle is close to minus 90 degrees, it is behaving more like a capacitor. And then you have everything in between. 45 degrees you can interpret as being more diffusional. But for instance, if I have just capacitance with a leading resistor, for instance, if you're looking at a supercapacitor, it might be something like this. It's like the simplest possible example. You can look at this data very quickly and say like, okay, well, at these frequencies, it's behaving, phase angle is 0. This is the frequencies of which it's behaving mostly like a resistor. There's a transitional sort of set of frequencies. And then over here at the lower frequencies, which makes sense if you understand how capacitors work to some degree, it's minus 90 degrees. This is behaving just like a capacitor. And if I have a lower alpha value, you might say it's like a capacitor, but it's not ideal. You see how you can correlate, for instance, having both plots, which is nice. The phase angle is not quite minus 90 degrees. It's like minus 80, minus 70, whatever. And the slope of my Nyquist plot line changes. So I can correlate those two things, but mostly I'm looking at the Bode plot. I'm looking at the phase angle because the values of the phase angle are instructive as to whether it's behaving more capacitive, more resistive, or maybe diffusion. diffusional or diffusionary, whatever the right word is. And then the last thing that I'll say is when it comes to circuit fitting, a lot of people focus entirely on the Nyquist plot when they're circuit fitting, either because their software doesn't show them both plots, which is one of the reasons why we show both in our software and our circuit fitting software here, Aftermath Blue. But also, it's dangerous to look at just the Nyquist plot when you're circuit fitting because you could be wildly off. I could probably illustrate that to a certain degree. So you might have a Nyquist plot, for instance, that is, let me see if I can. Even actually, this is pretty glaring. Like the Nyquist plot looks pretty good if you were to just like somehow tinker with it, or whatever. But look at the Bode plot; it's horrible. Like it's really quite bad. And one of the things that's really instructive and useful about the Bode plot, again, is the phase angle, what I call contours. Sometimes you'll hear me say this in these live streams at various times. It's how it changes direction. So it dips down and then dips back up and then dips down. So I'm often looking when I'm circuit fitting at basically the combination between the Nyquist plot, how well the Nyquist plot is fitting some of the key features like the semicircle or the transition between semicircle and line. And I'm looking at how the contours of the Bode plot fit, because by moving, for example, a capacitive element left and right, that dip in the blue trace moves left and right, and I could try to line that up, make sure that contour fits, try to make sure it follows the contours of my phase angle across all of the frequencies. And see, this is an example like parametric fitting. Well, the Nyquist plot still looks pretty good. I mean, it's a little bit off here, but for the most part, the key observation is that look at this phase angle. It's too high here, it's too low there, right? Okay, well, when I do unity, those contours like line up much nicer. I mean, it's not perfect, but it's pretty close. So those are my answers for the Bode plot. I tend to look really heavily, like Alex said, that like if there's one thing about the Bode plot, I really like to focus on the phase angle plot when I'm circuit fitting in particular and see how it matches more than the red line, because even in all of these different changes, it's harder to see any glaring differences in some cases. Now this one's maybe bad because you can see the red changing, but sometimes it's harder to see the impedance magnitude change really heavily because it's logarithmic. It just doesn't show changes as much. That's kind of what logarithmic scales, they can hide smaller changes because it's logarithmic. So that's a bit of an overview. Hopefully that kind of, I don't know, addresses some of the interesting points of Bode plots, and it might help you out there. Let's see.
Yeah.
Actually, yes, many avoided using Bode plots in their papers, even in our lab, but I found one highlighted it, and I wanted to know whether it conveys significant. Yeah, it certainly conveys significant info. I think one of the things is another just set of things I've noticed over the years is that some companies, for example, show you Bode plots with a positive phase angle, some show a negative phase angle. So that right there makes it difficult. It's like the convention's not the same. Well, that's annoying. So phase the phase angle is a peak when it goes down or goes up. It's kind of down, but it's not clear because it kind of goes up and down and up and down. So it's like, is that two peaks down or one peak up? It can be ambiguous. You kind of don't know what you're looking at. It's quicker to see a Nyquist plot and see, 1, 2 semicircles. Like I know what I got. Yeah. With a Bode plot, it's kind of like, I have some squiggles. I don't know what that is. So the more you work with it, the more you have it when you're fitting, the more you have your eyes on the Bode plot, the more you'll be accustomed to what those look like as well. And you'll be able to kind of rely on some of your own expertise and just experience looking at the Bode plot and what your data look like, in that context as well. So I would encourage you to use both plots.
Yeah, it's like Nyquist plots are useful because of just like pattern recognition. Humans are just good at recognizing certain patterns, and in Bode plots, there's no sometimes the pattern isn't very clear. We can't actually differentiate between them.
Not with that attitude.
Yeah. So the next question is actually from it might be for you as well. It's from LinkedIn. Akash is asking, gel polymer electrolyte or aqueous electrolyte to avoid dendrite formation, especially or at least particularly in battery systems. I don't know enough about battery systems.
Honestly, well, first of all, if it's like a lithium or a sodium battery, aqueous is not going to do you any good. Those are non-aqueous systems. So I'm assuming you're talking about just, I don't know, maybe an aqueous battery or I think as zinc. I think zinc is aqueous batteries. So there are some batteries that use aqueous systems, but something like lithium, one of the main concerns, for example, with lithium, maybe sodium too, though I don't know, to be honest, if it has the same struggles. But one of the reasons why I like lithium-ion batteries, for instance, use materials like transition metals, transition metal oxides for the cathode, lithiated transition metal oxides, and graphite for the anode. You'll notice that neither of those is pure lithium. You would think, well, why wouldn't I just use pure lithium for either or both of the like we couldn't use both, you'd have no voltage difference. But using pure lithium for at least one of the electrodes kind of stands to reason as like, well, it's an infinite lithium source. You might want to use that. It seems like it would make sense. The voltage would be right on the Li plus, etc. And one of the main reasons you can't is because you get dendrites. It tends to grow out. Dendrite is kind of like a spike that grows from one of the electrodes. It can pierce the membrane and cause a short. So lithium isn't even really safe to use by itself. It's kind of an odd situation. You'd think it should work. It doesn't. So as it relates to that, my knowledge of the difference in electrolytes, now I think all I can really say with some degree of certainty is that one of the reasons people are looking at different electrolytes, among other reasons, things like improving the voltage stability window, because some materials have like up to 5 volts and the electrolyte will decompose. So you're looking for ionic liquids that'll survive. And there's a lot of like that kind of stuff, stability. Some of them improve rate capabilities, different combinations of different electrolytes. All I can say is that it stands to reason that there is some correlation between electrolyte and dendrite formation, but I actually don't know a lot about that specific relationship. So to your question, I don't really know perfectly well whether a gel polymer or a liquid, let's say aqueous or non-aqueous, would be better in terms of avoiding dendrite formation. Actually, I'm not sure. The only thing that I know as well is that dendrites do tend to form at lower temperatures. So I don't know, maybe if one of those, let's say gel polymer, let's say if you're going to go to cold temperatures, the aqueous electrolyte is going to get close to its freezing point, and that's a problem. And maybe that's part of why the dendrites form at lower temperatures. Maybe a gel polymer is better in that situation. I don't know. I'm just spitballing and making a guess here. I don't know if that's the case. It could go the other way. There could be a perfectly valid explanation for the other way. I would have to look into the literature for that. So I guess directly speaking, I don't know really 100% which of those electrolytes is better to prevent dendrite formation. Again, I'm more familiar with the temperature dependence, I guess. Cold temperature is one of the things, that's why like electric cars, for example, have heaters. You think like, why would I heat my battery? It's not going to make it explode. It's like, well, at cold temperatures, if you cycle it a lot, it's in some cases more dangerous. So that's about all I can give you, Akash. I'm sorry I don't know more specifics on that. I'd have to look into the literature as far as like the relationships between electrolyte and dendrite formation effectively. I'm sure that there's some research on that, and it's just a little beyond my knowledge, to be honest.
All right. Got a lot of questions coming in, getting through them. Keep them coming, of course. Rana is asking, what's the difference between equivalent series resistance and charge transfer resistance in EIS, and where does it locate in the plots? Oh God, this is an EIS question I can actually answer.
You got it.
My God, it's like it's actually because it's like I know a little bit about this.
I don't think you need to say actually. I think you just can answer.
I can like just answer.
You don't have to be so mean to yourself.
I know, it's like
as though it's unusual that you would be able to answer.
Yeah, that's true. That's true. So clearly this is I'm not like not even an artist, good drawer, but like I can't even like this is that.
It's a beautiful drawing. Don't you worry.
I'm just warming up.
That's
warming
right.
up. But just gotta get the muscles moving. All right, so this is your what we call the series resistance. Let's just call it RS for series, and then we have RCT over here, which is the charge transfer resistance, and then this is like CDL. This is the common It's actually technically not a Randall circuit because a Randall circuit would have a Warburg element here.
Void element, yeah.
Void elements.
Yeah.
But void elements are just these.
I had to make that correction.
I know.
Someone made that, and I was like, ah, crap. They're
Nah.
right. I kept calling it a Randall's element. I was wrong.
Yeah.
It's technically not.
But when
Fair enough.
but when you have a circuit like this and you do EIS of it, if you have Z real on the x-axis, you have negative Z imaginary on the y-axis, you get a semicircle that looks usually something like this. It's kind of semicircle. And if you had the Warburg element here, then it would, that would shoot up. So the series resistance here manifests itself as the x-intercept at the high frequency region, and the charge transfer resistance manifests itself as the difference, if you will. So let me actually erase this circle here because this will make it a little bit easier for people to see. It's actually this distance here, and this would be the RCT, and this is the RS, and RS would be from 0 on the x-axis to this point. So this value is RS and this value is RCT. And one of the ways that we commonly teach, or we like to describe this to people, is in the high frequency region. So this is all high frequency. The impedance of a capacitor, 1 over j omega c, 1 over, oops, not minus, 1 over j omega c. As the frequency goes up, the impedance goes down. So in the high frequency region, this guy for the capacitor approaches 0. And when the impedance of the capacitor approaches 0, if I think about current moving through the circuit, the path of least resistance is through this resistor. It has to go through this resistor. And then it's just going to go through the capacitor. It wouldn't go through the charge transfer resistance because this is the path of least resistance. This acts as if I have a separate line here. So that's why the series resistance is just a high frequency x-axis intercept. It's when there's no other elements that change the negative imaginary impedance play a role. Now, on the converse, on the low frequency end, which would be here, call this low frequency. On this low frequency end, you have the opposite. So now the impedance starts to approach infinity because this value gets really, really, really small. Thus, the impedance of the capacitor gets really large. Now, the path of least resistance is through the charge transfer, is through the series resistance and through RCT. This is the path of least resistance. I'll use red to kind of draw what this path is. So that's why this path is both RS and RCT. This value here is RCT plus RS. So that is how, and let's just go back to your question just for clarification. Like what's the difference between the equivalent series and charge transfer resistances in EIS, and where does it locate on the plot? So that's where it locates on the plots. It's on this point and this point, and this is kind of physically what it is and what it represents. So Renat, I hope that this is helpful. Let us know if you have any further questions. I know there's I have a feeling there's probably a ton of extra questions that have probably come in since. Yeah,
there's actually 2 questions and different points here. So Ion has a question. Please explain how to find or fix the potential window for cyclic voltammetry. Is it the primary process for CV? And then a little bit later, Giri Sankar had a similar question: how to determine the potential window of a material in CV. Some material will show redox activity in negative potential, some in positive potential, specifically COF-based supercapacitive systems. So, I mean, that's another one of your highlights there.
Yeah.
So how to find the potential window in CV.
Window. Yeah. Let's go back.
I'm teeing you up. That's another one of your things.
Yeah. So finding the potential window in CV is sadly an exercise in trial and error, but there's a process that I will share with you. So often it's the case that your electrochemical system, and let's just say this is your CV, you have current on the y-axis, voltage on the x-axis. If you're working in a traditional 3-electrode system or cell, you may end up getting voltammograms that look something like this. This goes up, and then this goes down. Oh, sorry. Oh, can't draw voltammograms very well today. So this goes up, and then this goes down, and then it comes back up. So if I got a voltammogram that looks like this, I might say this between here and here is my potential window, right? And this potential window is only because, hey, after voltage is this high, I'm getting some high current associated with some process. And similarly, when I go to potentials lower than this, I'm getting some process here that is associated with one of a variety of different things. It has to do with the solvent. Actually, why am I typing this all out? I can just type it, when, especially if I'm...
I hate writing with the thing. With
I
the
know.
draw tool. I know it always. I'm always
It's
like, it's harder.
Yeah, so it's based on like the solvent, the electrolyte, and then the electrode materials, right? So just what is, these are the things that ultimately limit what your potential window is. Because the case that I drew here, you may often see this for like water, for example. Like this may be a glassy carbon disc, like a glassy carbon GC disc electrode, and this is proton reduction. This is 2H plus 2 electrons going to H2 gas. That's what that can be. And this could be what would this be? This would be water. This would be something like H2O plus like 4 electrons. Oh, no, a couple electrons, 2 electrons maybe. But anyway, this thing just generates protons, but a lot of like O2. I'm not doing the stoichiometry right, but you get oxygen evolution on this side of the reaction. But this is where water limits the potential window. If you did the same reaction in a cyanitrile, maybe it would look like this. And it goes all the way out, and you have a huge potential window here, right? And that's because I moved from water. I changed the solvent to a different solvent. This may be a cyanitrile, which is usually described with this symbol. But your electrode, you may be able to use like a boron doped diamond, and then you extend the potential window out, because these reactions that normally happen are due to the solvent don't react as easily on boron doped diamond versus glassy carbon. Platinum is probably one of the biggest examples. You can barely do very much chemistry on platinum from like a sweeping perspective, because platinum's got all kinds of like adsorbed hydrogen, reduction of platinum oxide. There's a lot of stuff that happens that makes it hard to analyze what's actually happening if you want to study your analyte material. So the way I like to recommend people to kind of do a potential window, to determine the potential window, is to do CV and start in a very small potential window. So only sweep from like here to here. And you'll get like a little box, and it'll be very little current passing. Okay, well then you expand the window out, and you get another box. Everything looks good. I haven't destroyed anything. Very little current is passing. My system seems to be stable. All right, let's extend it again. Okay, pretty good. Extend it again. Oh, wait a minute. Oh, I'm getting something there. And I'm getting something there. And these, I've kind of drawn them somewhat symmetric, but they might not be. They're, this last one could have actually, this last one, it might actually look something like this. It might be, here, and then, I just have to go a little bit to end up getting, current, reduction current or something. So just keep in mind that it could be your potential window may be asymmetric about, zero, or the open circuit potential. It can be zero. So you just start from like a small sweep limit and then slowly start to increase that until you hit the limit. That's probably the easiest empirical way to determine what the potential window is in your experiment. Now, this is I described it for like a regular 3 electrode cell, but I think you can do it also for supercapacitor systems as well. And I don't know enough about COF based supercapacitors.
Yeah, I don't know what that is actually, to be honest. COF.
Yeah, I don't know what COF is.
I meant to.
I hope you can.
Covalent of organic framework. Okay. Covalent of organic framework. Wow.
Organic molecules are made with covalent bonds.
Sounds like redundant to me.
Sounds redundant.
I don't know. It's probably just a big surface area sheet of something.
Yeah.
I
I don't want to make fun of the
chemically active. I want to make fun of it. It's silly. No, I have no idea. Yeah. That's not something I've a lot of experience with. But
yeah.
Anyway.
But yeah. I mean, that's
ionic organic.
Ionic organic. It's like metal organic frameworks. I'm like, okay, that
makes sense. That's a mixture of things.
It's like you have metal atoms that are connected with a molecule,
Yeah.
but they're in a network. I'm like, okay, I get that.
It's like, hey, did you know there's a hydrocarbon with covalent bonds? Can
Can
you believe it?
Can you believe it?
I'm shocked.
But
sorry.
Yeah, I know.
We're being very ridiculous.
Yeah, we're being very ridiculous. But hopefully that helps you determine what the potential window is, and what it's based on. It's based on all those things. So a little bit experimentation's required usually, because it's based on all those things. You can't do that many calculations to kind of figure out what it is, but experimentally is the best way to go about it.
Yeah, and there's so many things that will adjust that, like the pH of your solution and the reference electrode. So it's best to determine it experimentally most of the time.
Yeah.
All right, Ahmed has the next question, I think. So, hi, I'm working on solid polymer electrolytes with lithium salt. My cell is simply the electrolyte between 2 stainless steel electrodes, so no faradaic reactions. I would like to know how to circuit fit it. Well, the short answer is I can't tell you that without seeing your data. Obviously, I don't know what your data looks like, right? I would have to see it. What I can tell you is actually something of, I don't know, you say guess or a possibility. So one of the ways, actually, let me pull up, I did a webinar on something that would possibly help with this. So let's see, advanced, this one. It's the third one that I did. Sometimes when you have, this is sometimes called a symmetrical cell, where you intentionally make an electrode the same on both sides. And so you have what are called blocking conditions. Okay. So sometimes this is what you can have happen. Okay. You get what's called a transmission line. So the reasons why you would do something like this, and you might, please, Ahmed, fill in if this is what you're doing it for, but sometimes you're doing this to study the electrolyte. So you're taking faradaic processes, the actual charge discharge, processes out of the equation, or you're trying to study the membrane if you're trying to study transport properties. But like, you're taking the main kind of thing that you're doing it for out of the equation, which is the charge discharge, the lithium reactions, using stainless steel plates. There's no intercalation, deintercalation. And so what you're doing is you're studying the transport properties, the diffusional properties, or the porous properties of a membrane, or the electrodes of some kind, something like that. And so sometimes what you get is what's called a transmission line. And so because there are pores and you have transport of ions of solution in and out of those pores, you get this distribution of charge within a pore. And the way that that is manifested in a circuit fit context is through what's called a transmission line. So this is a transmission line model. It's you can see it's basically a semi-infinite, basically an infinite sum essentially of elements. You have resistive elements through either the electrolyte and or the electrode, or the metal material, and then you have interface at the boundaries. So the ZA and ZB here, which is the boundaries of my pore. And then you have this Y element, which is the interface between electrode and electrolyte within the pore. And this infinite sum, it basically captures the distribution of properties within the pore. Okay. This is taken from one of my webinars where I talked about it in terms of calculating what's called tortuosity. It's a kind of neat way you can do this using impedance data. But basically what the data often look like to accomplish this kind of fitting is something like this. Let me just quickly massage this and get it to look kind of like what I mean. So a lot of times when you have a blocking conditions, you don't have one of these might be open, these might be open or closed. And this is usually just capacitive. So it might look something like this. Let's see if this is what I want. So you might have something like this. This is a possibility. I'm not trusting any, I haven't messed too much with the parameters. Let's see, I could probably.
Ahmed also mentioned something. He said, yes, I'm trying to determine ionic conductivities.
Okay.
So transport and diffusion properties.
Okay. Yep. So that's what I suspected. So you might have something that looks something like this, where you have this like 45-degree kind of, this is the diffusional sort of behavior. Sometimes this is a Warburg open will fit this as well, but the transmission line captures this diffusional sort of 45-degree bit. Often is representative of diffusion. Sometimes it'll shoot straight up like this. I think if I make these short, that might fling it down. Let's see. Might cause this to change, hopefully. That's a bit wonky. This bit of our software is kind of neat, but it allows me to like play with the different transmission line. I can change the circuit as needed, and as you can see, I'm creating circuits that don't make any sense or do anything. So that's just one of the fun things you can do here. I don't know if I don't have enough perfect knowledge of what the best possible way to fit this is. I have pretty much all capacitive elements because you don't have any faradaic processes. So the circuit can look a little bizarre. You might have a half semicircle. Anyway, some of these might be what you get. I'm guessing if you're doing this, you probably have something like this, let's just say, where a lot of the plot that you're observing is to a large degree like straight up and down lines are at an angle. Okay. And so I just wanted to kind of point this one out, that the transmission line is one possibility of a way that you could fit that. But mostly because a lot of people maybe aren't as aware of the transmission line. It's a little bit of advanced kind of a thing. Again, the default or real answer, I guess I would say, is that I would need to see your data to be able to suggest like that model or other models precisely. But keep that in mind. Especially if there's pores, for transport within some porous structure of your whatever symmetrical cell, the transmission line can be really helpful for capturing that behavior. Otherwise, you might just have basically just CPEs or capacitive elements with some minor resistances to account for the, ohmic IR drop, those kinds of things.
All right. And similarly, continuing to talk about batteries, the next question is from Nav. Nav asks, which battery parameter can be selected or best choice for decreasing battery degradation, mostly during optimization in XEV, which I have.
It's electron volts. No, electric vehicles.
Oh, in electric vehicles. Oh, is that just the abbreviation for electric vehicles?
Yeah, I think I don't know what EVs. Well, typically I think it's like the EV is usually capitalized.
Yeah,
I'm not sure. X just sort of means like, I think it's like you see like XEV, like part of the electric vehicles, something like that. I don't know. I think I believe you're referring to electric vehicles is my guess. But either way, it's sort of a good general question. Like, what can we do to decrease battery degradation? So I think there's two ways to interpret your question. The first is by battery parameter, if you mean like the parameters related to the materials that I'm using, or the parameters related to the electrochemical testing of the battery, right? So those are different things. If it's the first part, like what parameters or properties, right?
Oh yeah, he's mentioned hybrid electric vehicles or electric vehicles.
Okay,
you're
okay.
Right. Yes.
So electric vehicles. Okay, perfect. Yeah, please feel free to comment, Nava.
Yeah.
You know, I basically laid out 2 interpretations of what you mean by battery parameters. Again, like properties of the materials I can adjust or you know, tinker with or pick materials, or parameters in terms of the testing, like charging, discharging, you know, what current, what voltage just to use. Those are 2 different ways to look at it. If it's the first one, that's a hard one to answer because there's so many possibilities. How can I prevent degradation? I mean, pick the right electrolyte. There's a lot of research on different electrolytes for different reasons, different, like for lithium ion battery, for instance, there's like a lot of different carbonates, ethylene carbonate, dimethyl, diethyl. A lot of people recommend some combination of like ratios of 1 or more or 2 or 3 of these different kinds of carbonates for various reasons. They provide different levels of stability or activity. So there's that stuff. You know, for battery degradation, a lot of times there is a trade-off in terms of the material you're using. Again, if that's what the parameters you're thinking of, as it relates to safety versus performance. So as a very quick and early example, it's less pertinent now. A lot of the new materials that are used are more developed than the early, but like the 2 earliest examples, for example, that like John Goodenough, you know, what is most famous for discovering and popularizing are lithium cobalt oxide and lithium iron phosphate as cathodes. And so, for example, lithium cobalt oxide has better power and energy density, but it's more dangerous. It's more likely to fail. Lithium iron phosphate has a lower energy that it can deliver, but it's way safer. It's almost impossible to get lithium iron phosphate to fail safety wise. So there's those kinds of considerations. So if you're trying to keep the battery from degrading, from failing, from having problems, sometimes it's going with a safer material. It looks like there was a comment. Did he say?
Yeah, he said most. Yes, mostly. I see
C-rate
people
or
use
SEI.
C-rate or
Okay.
SEI.
So I'll move on to the other idea about what parameters in terms of testing. Very broadly speaking, to prevent degradation, you're trying to avoid being overcharged or over discharged, right? So that's the very simplest and first, you know, important thing to be aware of. So if you're doing a test, you'll probably find some different interpretations of this in the literature or depending on who you talk to. But let's just say very, very, very generally, if I have 0 to 100%, I know my voltage limits of my materials, right? Okay, so I have, this is 0%. This is, pick the middle 90% of that. So cut 5% off of the voltage on either end, or 10% on either end, and work just in the middle voltages. Like, so you make sure that you definitely don't overcharge it, go too high in voltage. You definitely don't over discharge it, go too low in voltage. That's a way to prevent degradation for sure, right? And it's one of the reasons why, for instance, when your phone, I think this is still true. This used to be true at one point in time. I assume it's still true for a safety perspective, but like when your phone says it's at 0%, it's not. It still has some battery. It's lying to you. You know, your phone will shut off to prevent the battery from getting totally drained or whatever. But it's, I think for like the, again, I don't know if this is the case. I think for like safety reasons, there's still some power available if they had to, if you're, you know, it had to make an emergency call, like things like that. Like there will still be a little bit of battery, even when it says 0%, it's actually not quite 0, right? So some of those kinds of things you want to really avoid overcharging, over discharging. And that's by making sure the voltages are intelligently selected. C-rate, you know, SEI, those things, right? Very generally speaking, almost every material, maybe there's some as things advance and technology gets better, people are getting better at this. But one of the main problems, for example, with electric vehicles is the rate at which you can charge it, right? Which is why for a lot of typical applications, it's fine. You can drive it during the day as long as you're driving fewer than, I don't know, let's just say 400 or 500 kilometers. It could probably be fine on one charge. Put it in your house at night or your apartment, or whatever, charge it up overnight over 7-8 hours, and then you're good to go for the next day. But what if like a gas station, you know, you can pull your petrol or gasoline or diesel powered vehicle into a gas station and charge it up, right? With fuel in under, it's like 4 minutes is the time. It's 3 or 4 minutes. 3 or 4 minutes is something like 12, 13, 15 C. when you do the math, right? So when we're looking at an analogous situation for electric vehicles to meet infrastructure and capabilities of, petrochemical powered vehicles, it's like, can you charge it at 15C? And of course, that's another point to your question. Well, how do you make a battery degrade really fast? Charge it or discharge it really fast. The more that you charge and discharge any battery at high C rates, the much quicker it will degrade. Again, some technologies are trying to help fix that, but as far as I'm aware, there's no really good way to take a material and be able to charge and discharge it at like 10C, like a million times over 10 years, and it doesn't just lose its capacity entirely and be completely unable to function anymore. So very fast. Now that's unavoidable with EVs, right? Of course, you have to accelerate very fast. It requires a very quick discharge, but hopefully it's not for a long period of time. Things like that, right? The slower, generally speaking, that you can charge or discharge a battery, the more degradation you will prevent. So that's the name of the game with EVs, generally speaking, is trying to find batteries that survive better under those conditions, or find ways to operate them without having to discharge or charge them super quickly.
Yeah, Nav has a kind of, I guess, a follow-up comment. It's like he wants to know, like, what if you want to control charge? I mean, you just talked about this. You want to control charging and discharging in a way where you can sometimes use battery aggressively, but still want to decrease degradation. And in case what, in that case, what parameters? Which it sounds like for you, it's like kind of dynamically changing the C rate, if you will.
To a certain extent, if you need to aggressively use your battery, you can do that. You just have, if you're trying to improve longevity and decrease degradation, you will just need to limit as much as possible the amount of time that you are aggressively charging or discharging. Those are trade-offs. That's not to say you can't, even a commercial battery that's not designed well to handle fast charge or discharge can be charged or discharged quickly in short bits or once or twice. Like it's, but the more you do it, the more you're going to degrade the battery and decrease its life. This is just, if you're looking for some, perfect answer of like, well, this is how you can super quickly discharge or charge your battery and not have any degradation at all, that isn't really like thermodynamically possible. It's a trade-off between degradation and speed that you can just. Now again, there's methods I've read about, like pulse methods. Some people have advocated for things like, if you do different like pulsing to charge, you can it's interspersed with like a GITT kind of an experiment. Maybe that can help recover or help the battery last longer. There's things like that. So if you're going to use it, maybe if you have aggressive use, pulsing, like not just C over like 50C, like, right, as much as you can, like do it and then release, do it, like it's almost like pumping it, interspersed with open circuit. Maybe that will help. There's other ways that people have looked at, like morphology, and the first thing that I talked about, like different material preparation that can, different polymer electrolytes maybe can handle fast discharge without degrading a little. There's people are working on it. Like this is the thing people are constantly working on, right? And it obviously works to a certain extent. Like electric cars are all over the road. Like we have electric cars, so it isn't as though it isn't possible. We've reached this point technologically, like society, like, which is good. But to a very large fundamental degree, there is just a trade-off between these two things. Very fast application of a battery, charging or discharging, will degrade it faster. It just will. You cannot avoid that reality. That's science. So
yeah. That's science.
Yeah.
Unless there's some breakthrough.
Unless science changes, I'm willing to change my mind. But that, as far as I'm aware of it, that is science.
So the next question, gotta go back up. We're getting a lot of new questions. Shivram's asking for OER, oxygen evolution reaction, when we should measure impedance after how many cycles we need to activate the sample. It's a little hard to understand the question a bit, but I think what you're asking is like, when should you be measuring EIS for your OER system, especially if you have a catalyst and you're trying to activate the catalyst? And I think it depends on what you're trying to do. I think there's value in doing EIS prior to doing any cycles. And there's also value in doing EIS after you've done cycles to, quote, activate your sample. You'll observe changes in the Nyquist plot that will hopefully teach you something about your system. You may even want to do EIS after you've used your catalyst, after doing electrocatalysis, or even during electrocatalysis, you may want to do EIS. So I guess I can't answer your question in a very like exact way, because it's actually not even a question. It's just kind of saying like after how many cycles you need to activate. But you'll get different information depending on not only after doing so many cycles, but at what potential are you collecting EIS at? So there's both what you're doing to the sample before or after or during, cycling, catalysis, stuff like that. And then the potential with which you're collecting the EIS. So you can collect it at open circuit potential, which might not give you a whole lot of information at all. You can do it at a potential that is close to the oxygen evolution reduction reaction. You can do it at OCP after doing so many cycles. You may see some interesting differences in the Nyquist plot that can tell you information about your catalyst. So that's how I would approach your question. I guess the situation of doing OER and measuring impedance. But Shivram, give us a few more comments about what you're really after, and we can talk a little bit more about this. All right, so we answered. I think we answered
Yes.
Girasankar's question. Mervet is next. And Mervet's asking, as the semicircle diameter decreases, it means the system is less resistive. So having a depressed semicircle is better than the broad semicircle in terms of resistivity as well? Question mark. I would say no. So you're looking at, I'll just share screen, and Neil, of course, talk or chime in as well. This is how I'm kind of looking or thinking about that question. Is it's like, oh, you have so you have your semicircle. You have one semicircle which is normal, and this is Z real. And then you have Z imaginary, negative Z imaginary. And then let's say you also have another one, but maybe it's like depressed. This is a big exaggeration.
Mm-hmm.
But what I think is that you have kind of two different mechanisms, and the RCT, which is here, if these widths are the same, then the charge transfer then the resistance is the same. But the mechanism with which you get these is probably very different. This can actually be from, you could have multiple charge transfer. This could actually be the combination of multiple charge transfer, semicircles and stuff.
Yeah, or it could be a very non-ideal process.
Or it's a very non-ideal process. Yeah,
the alpha is
the alpha value in your CPE is different. This thing can change. Its alpha value can go for a variety of different values. Where this one, the alpha is just equal to 1, or it's a capacitor. So that's how I think about it. I think it's just like the total resistance. There can be deconvolutions in what actually is the system. but the depression doesn't. I don't think it tells you very much. Like unless you have a pure semicircle, and one thing to mention about semicircles is like, hey, if this is the radius, it's like it should be equidistant on like both sides. So if you have a semicircle that only goes up to here, for example, the distance from here to here should be equal to the distance from here to here if it's a actual semicircle, and vice versa. These distances all need to be the same. So even if you have semicircles where part of it, this part, it becomes a Warburg tail after that, it should be the same length all around for a perfect semicircle, or if you have a perfect circle in general. So just something to keep in mind. If it's depressed, I think you have a different mechanism going on.
Yeah, or it's just really non-ideal, but the resistance can be the same.
Yeah.
Yeah.
So hopefully, Mert, that helps.
Giri Sankar has another question.
Yes.
How to fit a Nyquist plot with half semicircle with a Warburg component? Probably with a Randall's element. I don't know if that's the question, if there's something more I'm missing here.
Well, a half is when he says a half semicircle, he's talking about like a quarter circle, because when we say a semicircle, that's half of a circle.
So a semicircle?
A semicircle, right?
It's actually kind of like the example I was showing before.
Yeah.
Just happenstance. Where is it? Was it this one? Yeah. So you might have something that looks like this, where it's like, hey, look, it's like a semicircle, but it's like semicircle. It's like this doesn't finish entirely.
Mm-hmm.
So maybe that's kind of what you're talking about. And then there's a Warburg element. And so, I mean, you can fit this. I don't even know. I think I picked a Warburg. You can, let me make a new circuit fit. I mean, you could fit this with a Randall's circuit or a Warburg element, but it's this, right? This is the Randall's. If this Q2 is like a Warburg with a alpha is 0.5, you can just fit this kind of behavior with a simple Randall's circuit. So I have to change the value there and I can get a fit. So like that's how this can be fit pretty easily. I don't know if you have a more complex part of your question, but basically if you have some part of a semicircle with a tail, like a Warburg tail, you can just fit it with a standard Randall circuit. It should be all right. You don't, as long as there's enough of the semicircle sort of formed that it, there has to be a little bit of inflection almost right between the semicircle, and like if it's just straight up, it's like, it could be hard to find the semicircle, but as long as there's enough distinction there, you can fit it. The circuit fit will account for those, even though it's not fully formed, so you don't have to have a full semicircle, right? It's not always going to happen because of just whatever the time constant happens to be. So
the next question, I don't think either of us know the answer to this, but might as well just mention. Dumbo123 is asking, can you explain mem resistor switching mechanisms? Is this still part of the electrochemistry topic? So
it's more physics or electrical engineering, I think.
Yeah,
I'm not sure. I know the term like memristor or mem resistor. I think, is it memristor? That's a thing. Like memristor. I know it's like almost like a resistor.
I looked it up, and it looks like it's in the semiconductor world, which is part of technically part of.
Is it just a diode?
Electrochemistry.
It's not a diode. Exactly.
According to Wikipedia, it's like it's this complex nonlinear resistor type of thing that involves like magnetic flux.
Oh yeah,
I don't know anything about it.
I got nothing, Dumbo. Very sorry. Not something I'm familiar with.
It's like I couldn't explain it, and I couldn't even tell you about the switching mechanism.
All I can tell you is what Wikipedia just told me.
Yeah,
which is not helpful. So
have to.
That is not something I'm aware of that's used in electrochemistry. It's not to say that it isn't, but I don't know of anybody who uses it in electrochemistry.
That is the first time I've ever heard that word before.
I've heard it.
I've never heard it.
It's probably the first time I've ever said it out loud.
Oh, okay.
Because saying memristor sounds like I'm trying to say resistor, and it's getting stuck in my mouth.
Yeah.
Because I've seen that word before, and it was like, oh, that's a weird thing.
Yeah.
Like, whatever. Yeah, I don't know. I think it's like somewhat new. If that's straight. Like,
I bet our electrical engineers have heard about it and know about it.
I might be totally making this up, so this might be complete nonsense. But I think it's like we have resistors, capacitors, and inductors, like
Yeah.
the fundamental whatever, like
Yeah.
electrical circuit elements, right?
Mhm.
I feel like there's like thermistors or thermos. That's a thing.
That's the thing.
And then there's
Okay.
memristors, or you know, I feel like those, like I remember seeing, you know, like almost like a Scientific American, or like some like news thing in the last not 4,000 years, you know what I mean, like relatively recently, where it was like, hey, there's a new electrical component people are using for whatever. That could be totally wrong, and I might be confusing it with something else, but I feel like it's somewhat of a new phenomenon. You're looking at me like I'm nuts.
I'm
You're like,
just,
what is he talking
no,
about?
I'm literally, you're on a train where you could just tell me like, you know, I saw it in Scientific America along with like memzap flux capacitor
Yeah,
thing,
it's
and
this
it's just like,
crazy thing.
it's totally a thing, Alex. And I'm just like,
Yeah, a gorboflaptron. It's
Flaptron.
this amazing new device.
Yeah.
I feel like it's a thing. Like one of those or both of them, they're like relatively new to the scene of electricity. I'm done. I don't know.
What was that thing? No, what was that commercial with oh God, you know what I'm talking about. We had the it was for the old podcast, and it was like that profession, it was like a very professional looking thing where a guy literally was making up every single like technical word about like the Graphite 3000 utilizes, you know, what is it?
The
Do you know?
oh, I know what you're talking about. Yeah. I made the parody thing of it or
Yes,
whatever. It's
yeah.
like oh my gosh. Go to the next question. I'll find it.
Yeah, I forgot what is. That might be a fun thing. But yeah, I can actually talk about the next question because I know what the next question is. I know the answer to this one. So Ayan is asking, what is open circuit potential and how should we select it? So the open circuit potential, and I can do some drawings of this as well. The the terrible definition that is often used and described is it is the potential at open circuit, and that's not terribly helpful for lots of people. So let me delete this whole thing. So if you have, say, so if you had like some kind of voltmeter over here,
I found it.
you found it. Okay,
We're gonna play it after this.
yes,
it's the best 2 minutes and 1 second you'll ever watch.
so open circuit potential, OCP, and I don't know why I drew these like this for some reason. My brain's not. But these are two electrodes, and the open circuit potential, and I wish the eraser tool, small erase. There we go. So the open circuit potential is literally like, oh, what's the potential quote at open circuit? Why was that not thick that time? It's like when this is disconnected, open circuit, what is the potential difference? What is this voltmeter reading? So that's, of course, not really what happens. You do have to have a connection here to make it, but there's a very large resistor in here, super, super large, such that a tiny, tiny amount of current passes between these two electrodes. And we can, so much so that it does not really change the potential difference between these two. And the best way that I like to think about the open circuit potential from a standard like 3 electrode cell configuration is if you have a working electrode. So this is working. And let's make it simple. Let's just forget the counter for right now, and let's just put a reference electrode. And reference electrode. And if you were to put a voltmeter between these two, that would also be a measure of the open circuit potential. And what it is, what is it measuring in this case, is it's measuring, you could say, the, if you will, the inner potential of the metal electrode. So it's the potential of the metal. I'll make this a little bit bigger. So we usually use phi. So it's like the phi of the metal minus phi of the solution, because that's the interface, the metal solution interface. And then minus the same thing for the reference electrode, but the reference electrode potential, we'll just call it phi ref. And phi ref is still kind of made up of this, but this is just the, like, this is what the double layer is in an electrochemical cell. So the potential of the metal electrode minus the potential of the reference electrode at when no current is passing. So this is an important part of this, is that's the potential where no current is passing. So this, the open circuit potential, is a great potential to start when you're doing a cyclic voltammetry experiment. You should start the open circuit potential. You should start sweeping at a potential where nothing is happening, no current is passing. And then you can go left and right. Now, to change the open circuit potential, you have to change things about the system. You have to change the solution. You have to change the reference electrode, which is perfectly fine. But those are ways you can, quote, change the open circuit potential. And the open circuit potential can change during the course of your experiment because the solution potential, the potential of the metal, the system needs to equilibrate. So open circuit potentials can change over time. But that is the kind of simple and short answer of like what is open circuit potential and how you select it. So you don't really select it, but you just measure it. You want to share this?
We're gonna do this.
Yeah, we're gonna do a quick
diversion for 2 minutes to the funniest video.
Yeah,
if you're a nerd, but I love it.
Yeah. Right. I think you'll all appreciate this.
It's my favorite. I gotta share the audio. All right.
Oh yeah.
So this is a video. This is the jargon, like the perfect jargon that you can possibly have. So this.
Here at Rockwell Automation's world headquarters, research has been proceeding to develop a line of automation products that establishes new standards for quality, technological leadership, and operating excellence. With customer success as our primary focus, work has been proceeding on the crudely conceived idea of an instrument that would not only provide inverse reactive current for use in unilateral phase detractors, but would also be capable of automatically synchronizing cardinal gram meters. Such an instrument comprised of Dodge gears and bearings, Reliant electric motors, Allen Bradley controls, and all monitored by Rockwell software is Rockwell Automation's retroencabulator. Now basically, the only new principle involved is that instead of power being generated by the relative motion of conductors and fluxes, it's produced by the modial interaction of magneto-reluctance and capacitive diractance. The original machine had a base plate of prefamulated amulite surmounted by a malleable logarithmic casing in such a way that the two spurving bearings were in a direct line with a panometric fam. The lineup consisted simply of 6 hydrocoptic Marsal vanes, so fitted to the ambifacient lunar wane shaft that side fumbling was effectively prevented. The main winding was of the normal Lotus-O deltoid type placed in panendermic semi-boloid slots of the stator. Every 7th conductor being connected by a non-reversible Tremi pipe to the differential girdle spring on the up end of the gram meters.
Girdle spring.
Moreover, whenever fluorescent score motion is required, it may also be employed in conjunction with a drawn reciprocation dingle arm to reduce sinusoidal depleneration. The retroencabulator has now reached a high level of development, and it's being successfully used in the operation of Milford trunnions. It's available soon wherever Rockwell Automation products are sold.
How did this guy do that in one take?
I know.
Like
I know.
I can't even believe that. I was just impressed. Like that's some acting.
That is some acting.
That's a script to memorize, and that is just some acting to not smile as you say the most ridiculous made-up jargon.
Oh yeah. That's just. I hope you guys enjoyed that. Hopefully, we also don't get some kind of like YouTube copyright strike or something.
We're just showing a video.
Yeah. It's not like we're
a retroencabulator.
Retroencabulator.
Also, I don't want to let the cat out of the bag, but it's not a real product.
It's not a real product.
So okay. Oh man, that one always gets me. All right, so
hopefully you all enjoyed that.
So Ahmed had clarified about the blocking condition thing there, trying to determine ionic properties. Yeah, so he said, thank you so much. My confusion is that Warburg is usually for diffusion limited charge transfer. No, it's just diffusion. Warburg is definitionally the impedance of diffusion, not charge transfer necessarily. It can have some crossover, like in certain contexts, like there's Warburg short, for example, you can kind of correlate with charge transfer in some ways, but no, I wouldn't expect there to be any charge transfer for you, period, at any voltage or frequency or anything. If you have stainless steel blocking electrodes, electrolyte There's no faradaic processes that occur. All that's going to happen is diffusion and capacitance, basically. And so no, I would not expect there to be any charge transfer. It just seems pretty cut and dry if you've constructed your blocking system appropriately, I guess. There could be some side reactions. There could be something, I suppose. You could rip apart the electrolyte. That's a faradaic process. So it's not impossible, but the point of a blocking, condition cell is to largely eliminate faradaic charge transfer kinds of processes. So,
I guess I've always thought that like there was a charge transfer process always.
what is it?
Well, so it's like
Unless you're calling like the capacitance setting up a transfer of charge. I mean, that kind of is. I just there's no like RCT. Like what is it? What's the faradaic
like
process?
in the case of his where he has like,
Yeah, like
he
a
has
blocking
two
condition.
stainless steel things. Okay, so he has two stainless steel things with an electrolyte in
You'll have
between,
like lithium ions.
and he's also getting. So wait, so those lithium ions.
Yeah,
the
like it's
lithium-
like so if you have a lithium ion battery, right? You have
Yeah.
like LiPF6, right? In
Yeah.
carbonate electrolyte. So you have
Yeah.
lithium ions that are moving back and forth.
Yeah.
But on both sides, you have just metal. There's no intercalation, there's no deintercalation. The lithium can't go in or out of anywhere. All it can do is just set up a double layer on both sides or whatever. I guess there could be a passivation layer if it's steel, like those kinds of things. But like,
That's separate from like the current collectors, right?
yeah, like you
Okay.
could use just copper and aluminum, maybe,
Yeah.
like with no cathode or anode on them. That's one possibility. Or you could just use steel at both sides. And all you're doing when you change the potential is, I guess, sort of forcing migration of something across in one way or the other, maybe. Like if one of them's positively charged and the other's
Yeah.
negative by applying a potential, the ions will draw towards the negative, like the lithium will go towards the negative side, or
Yeah.
something like that, I guess. Like,
yeah,
but what
that's-
what charge transfer or faradaic process is going to occur other than just stuff moving?
So, but would that be like a migration thing? Because it's like, oh, I have an electric field and I'm moving something due to an electric field, so I have migration
Yeah,
that's
good.
pulling the charge, but I don't have the charge transfer at that point. I'm just moving the charge molecule. I've always thought in batteries there's always like an electron transfer that's occurring at the
But it's not a
interface.
battery, really. There's no anode.
Oh,
with
in
them.
in
That's
his particular case,
yeah,
it's
like
not
in a blocking condition. You're
Oh.
right, in a battery, of
in
course.
a battery. Okay,
But when
in
you
his
take
case.
the anode and the cathode away, all you're doing is studying the transport. Now, whether it's migration or what's causing the stuff to diffuse and move, I don't know. That's a question. I'd have to think about it. We could
Yeah.
probably talk through it. But there's no, like the Li plus an electron gives you Li, like
Yeah.
LiC6. Like that's a faradaic process, right?
Yeah,
It's
that's
a
a
reduction
faradaic
reaction or
process.
an oxidation reaction, depending which way you're going. Like, oh, yeah, that's a charge transfer
Yeah.
process very clearly, right? But you take the carbon away, it can't do that.
You can't
So
do
the
that.
Li is just going to make a double layer or something, or
Something like that.
diffuse. I mean, diffusion's happening all the time.
Yeah.
I should put the
Yeah.
the thing here.
yeah.
But,
that's right.
but it's gonna, maybe it diffuses within the membrane. There's a porous structure. Like there's
Yeah.
things you could talk about here, but it's not
Interesting.
intercalating, so there's no faradaic.
Yeah,
charge
there's
transfer
no electron
process.
transfer. Okay.
Anyway,
All right.
um,
I'll think about that.
a few
Lots
other
more,
sort of
but
comments on
that's
the
good.
COFs. So Giri Sankar says, don't want to get surprised. I'm not surprised. COF materials are extensively used for energy storage applications by introducing redox active sites. There's 10 JAX articles per week. I guess it's a bigger deal than I know. And TT sort of echoes that. Says COFs are composed of light elements, not metals, connected to the organic molecules by covalent bonds, unlike metal organic frameworks that use metals connected to the linkers by coordination bonds. So it's called COFs. Interesting. Okay, cool.
Yeah.
It's not a, that's, I appreciate it. We're being silly before.
Well, yeah, and I
Wasn't trying to
haven't,
denigrate an entire field of science, to be clear. We're just being stupid and funny.
and truly, I had not heard about it, and
I'm not aware of it either.
like I looked at it on Wikipedia. I'm like, oh, it was discovered in like 2004, 2005.
Just like thermistors and memmistors.
Mr. Ben.
Yeah, it's probably the same scientific retroencabulator article that I read. That was the same one. Now that you mention it,
Okay.
and it all comes back. So
Okay.
that's in the biz. That's a callback. You know what I mean? For like stand-up comedy, it's a callback.
It's a callback.
See what it did there. All right, Shizil from LinkedIn. Thank you for being patient. We're being a little silly today, but asks C rate, I think, or current density, which is a better battery term. I prefer C rate, to be honest. C rate is more current density is specific, right? It's current because that's what the density means, like how many milliamps per centimeter squared. So it's area specific. I don't think that's helpful because C rate is kind of intrinsically mass specific. And you can have surface area with different masses, and then the current density doesn't mean anything. Because you have a surface area, but how much stuff do you have? Because the ability of a battery to charge and discharge to do its thing is dependent on how it's really more intricately tied to the mass of the material that you have. That's what determines the power density. The density often is either by volume or by mass more than current density, like with a surface area. Like that plays a role a lot of times in RDE and things like that. But with batteries, I would prefer C rate. And then I think there was a follow-up with how is theoretical capacity of a material calculated? It is a pure theoretical value. Let me show you. I like to do this for some reason. I really like this kind of once I learned this, I kind of was like, oh, it's so simple. You can't believe how simple it is actually. Mm-hmm. So for example, you may be aware that graphite, right? Graphite, carbon, right? Which often is it's a ring, right? I think technically it's like a ring of six carbons, so whatever. Its theoretical capacity, specific capacity is, you might know this number if you're familiar with batteries. It's 372 milliamp hours per gram. That's the theoretical capacity of graphite. How do I get that number? I'll show you. It is actually literally just the formula weight. That's it. You're done. No, well, there's some math involved, but I want you to know it's actually quite simple. So the molecular weight of C6 is 12, right? 12 times 6. 12 times 6. So 72. Yeah. So it's 72 grams per mole. I'm going to write that upside down. So this right here is just the formula weight of C6. So I'll put moles of C6 per grams of C6, technically speaking, right? That is just the formula weight. All right, let's take a quick diversion. What is the equation for the intercalation of, this is an anode material, right? So the reaction that occurs is Li plus an electron. It's actually like X, we talk about the intercalation, but I'll just make this like the simplest possible stoichiometry that I can for the purposes of this calculation. Plus a C6 gives me Li C6, right? Li plus, sorry. So a lithium ion with an electron, intercalates with graphite carbon ring and gives LiC6. So now what I'm going to do is I'm just going to use stoichiometry. For every 1 mole of C6, how many moles of electrons do I have? Well, it's obvious, 1, right? So I'm just using the stoichiometry of this expression that I wrote over there. 1 mole of electrons per 1 mole of C6. It's a 1-to-1 ratio, very simple. Next, Faraday's constant. There are 96,000, numbers are hard. 9645.3 is the number I learned. I don't know, it might be slightly different. Mm-hmm. Coulombs per 1 mole of electron. This is just Faraday's constant. And then I have one final calculation to add here, which is by multiplying by the number 1 in the following form. There are 3,600 seconds in 1 hour. And I'll show you why that matters in a second. Let's just do the crossing out of units before we do numbers, right? We have a mole of C6. Let me use a different color so it's obvious. Mole of C6 cancels. We have moles of electrons that cancels. Not C, this is stupid. Carbon, and this is coulombs, so apologies. This is not carbon. This right here is coulomb, so I'll cross it out that way. Coulomb per second. What's a coulomb per second? That's an amp, right? Coulomb, I should use a different color. I'm going to uncross it out so I can, oh no, I just crashed PowerPoint.
Oh wait, it's because if you do undo like 2
undo,
times.
I hate this. Sorry, I will get it back in a second. PowerPoint likes to crash when I undo things. What a pain in the neck.
Oh, I know.
Let's see if it pulls it back up. I don't think it's gonna. I'm gonna have to read. Let's see. Did it save my scribbles? I don't think it did. Pulled up. Oh, it did.
It did. Okay.
Ha!
Nice.
Okay, good. I will.
All right,
I will
you can
resave it. I will
reshare.
reshare. Apologies. My this happens for me from time to time. It recovered my scribbles, so that's good.
Yeah.
Close this. Okay. I'm not gonna ever undo ever again. I'm tired of. I don't know. It's such a dumb thing. Why does that happen? Please explain. Anyway, I'm not sure what there's like extra scribbles here. Okay. As I was saying, moles of C6 goes away. Moles of electron goes away. I have coulombs per second. That's a unit. That is equal to amps. All right. So what am I left with, right? I have amps times hours over grams of C6, but grams, right? Now let's just do the math. So I know you can't see this. I'm just pulling up my calculator here. So I have 1 over 72 times 9645.3 divided by 3600. And that gives me 0.372. That's it. So I just multiply by 1,000 to get 372 milliamps. That's it. That's where this comes from. Yep. That's the number. So to your question, Shijiel, I think the theoretical capacity of a material is literally related to itself, its capacity, its mass, and then its stoichiometry with how it intercalates. Now that's going to vary for different materials, for its stoichiometry for how it intercalates or holds lithium or whatever. But it's quite simple. So hopefully that kind of shows you where that comes from.
Okay. See. Yeah. I think he had one more.
Yeah, there's another question.
One more question.
Can I use self-discharge test for having an idea about the polysulfide shuttling in a lithium sulfur battery? I have no idea.
Polysulfide shuttling?
Self-discharge for polysulfide. The only thing I know about lithium sulfur batteries is that there's like 5 billion like states. I really don't know a lot about lithium sulfur batteries, except that like the way I just showed, like LiC6, like it's really simple. It's like 50% is like, you'd be like 0.5 Li plus 0.5 E. Like it's like LiX C6, and it's just X goes from 0 to 1. It's like a very simple conceptually, like stoichiometrically or whatever. And lithium sulfur batteries, it's like LiS, Li2S, Li3S7, LiS19, Li14S22. It's crazy. Like, just pull up the first paper that comes anywhere of lithium sulfur batteries, and it's like the number of like oxidation levels and stages that it goes through is wild. I've never worked on them. I never studied them. So it's a great question. I honestly don't know. I don't know. I don't know enough to answer that question. It's a really good question. I just don't know. And all I know is, like I said, that lithium sulfur batteries are wild. It's a lot. There's a lot there. And that's about all I can say. So yeah, sorry. I don't know.
He has more questions, but there was another set of questions that came in from Jesse Mentor, who asked, for liquid electrolytes versus solid state electrolyte, does the frequency matter for potentiostatic EIS? I'm finding for the low frequency going from 1 millihertz to 1 millihertz, the Nyquist plot starts to get noisy. It's not a big range. And just as I find that at lower frequency, the next loss becomes noisy. It's a semicircle, but a noisy semicircle towards the end. And it does not surprise me that as you go to lower frequencies, or just being at a low frequency, you're going to get noise because it becomes less stable. I think that's both for liquid and solid electrolytes. You're going to observe instability at the very, very low frequencies. It's just so
you're gonna have
easy.
drift no matter what you do. It's good. I don't know which one would be worse. I mean, honestly, it's a thought process. I have to think about it. I don't know. I've done mostly liquid systems, so I don't have a lot of experience with like solid state. Generally speaking, solid state electrolytes improve your ability to get high frequency information.
Mhm.
Like solid state systems, you can get like above a megahertz. You know, there are processes that are really fast in solid state systems. Diffusion and liquid phase, you know, stuff can be kind of slow-ish, I guess.
Yeah.
So people like solid state systems because it's faster. And so with faster processes, faster time constants, or smaller time constants, or you want to say faster processes, you have to use higher frequencies to probe those. And so solid state systems are for that. So as a logic exercise, my guess is that slower frequencies would struggle more at a system that's more designed for fast. But that could be wrong. I don't know.
Yeah.
You know, that's just my hunch. But even so, let's just say, for argument's sake, that possibly liquid systems are better for slow. You're still going to reach a point where it's noisy. That's unavoidable. You don't have to probe to finish the semicircle. Like if you're trying to finish your semicircle by probing down to a millihertz, first of all, it's going to take forever. But secondly, you don't have to. Like, you don't have to fit it. Now, maybe there's some process you're really trying to probe at low frequencies, in which case that's just tough. Like, that's just, it's you're going to be up against it. It's really hard to keep a system stable as you're probing it at that small frequency, because it has to stay perfectly stable, linear, and causal to be valid impedance for like a half an hour while you're doing one super slow frequency. You know, it's agonizingly slow. So, in most cases, you often don't need to resolve data that low. Now, again, I mean, maybe in your case you really do for one reason or another, and that's fine. But 1 millihertz to 1 megahertz, that low range is where you're going to have that issue, right? Of course. So I think don't be discouraged by it. I mean, just cut off. My suggestion is that if practically it's not possible, cut off your frequency where it starts to have outlier points, and just, you know, focus on the area where you can. And, you know, circuit fitting, as long as you have some portion of like features of semicircle, there's a natural extrapolation from circuit fitting. Like, you don't have to have a full semicircle to get a fit of a void element or a Randall's element. It'll still fit in a lot of cases.
Yeah, I'm just looking at kind of the next set of questions. I think that's gonna. He also clarifies like one millihertz to 1 megahertz.
Right. I saw that.
Frequency,
Yeah,
but it's like,
but the low end being the problem makes sense. Yeah.
Shijil has another question, but there's also there are actually two questions. He's asking, can I use GITT for diffusion analysis in any conventional chemistry, or is it restricted only for intercalation? If yes, no, why? And other methods can you suggest for lithium sulfur conversion chemistry? There's another question later. No. It's a different Shijil, unless the pictures are exactly the same, but the last names are different. But it's the same question. Is GITT restricted to intercalation chemistry for diffusion kinetics, or can I use it for lithium sulfur chemistry? I want to say this is the same person. It's like, come on, are there going to be two Shijils
or three Shijils
asking about the same chemistry on this podcast?
This is
at any given
coincidental.
This is too coincidental.
I don't know.
I'm a little bit like, I suspect this is the same person.
This is the same question. I don't know the answer to. I don't know. It's like you're trying to like,
but I don't know.
Clone yourself to ask the same question multiple times.
Which I get. You know, we're on LinkedIn. One's on LinkedIn. One's on YouTube.
Maybe that's the point.
He may think that we responded in kind of odd orders.
That's true.
But
well, in any case, we'll answer the question, or I'll do my best.
I
do not think that GITT is limited to intercalation. I do think you should be able to get diffusion coefficients for a conversion reaction. Fundamentally, GITT, PIT, any of these intermittent titration techniques. There's another one that I was going to bring up. It actually is a bit of a shameless plug for my PhD work and my group. This was a paper where I used what's called a current pulse relaxation. It's similar to GITT. If I remember properly, I'd have to remind myself. I mean, I wrote the paper, but I don't remember. it the best. It's like short pulses followed by the GITT and PIT have similar kind of phenomena. You pulse for a short bit of current basically, and then you let it relax, and the change in the open circuit potential, how it responds, if it gives you information about the diffusion coefficient. So current pulse relaxation, you could look up this technique. It's a similar phenomenon to GITT, but not exactly the same. And so that's another method. But the diffusion coefficient, you can also calculate it using impedance. It can be a little tricky to get. Sometimes the accuracy is tough because it requires you to have a good circuit fit. If you can't get a good circuit fit with your Warburg element, well, is that accurate or not? There's open questions there. But to the best of my knowledge, my impression is that the GITT, the PIT, this kind of titration technique, whether it's a intercalation or a conversion or an alloying reaction, you are fundamentally drawing the pulse of the current or whatever is, you have a reagent diffusing all around. So you have a diffusion layer. You have some that are very close to the surface in your material, whether it's intercalating or conversion reaction, whatever, or it's or they're far away. The pulse, applying a current or a potential or whatever it is, draws the solution is going to get the reagents are getting drawn in, and then the releasing, it's the idea is that they're relaxing and moving away. Like you're measuring how they diffuse away when you've stopped, but that doesn't mean they have to have intercalated. There's a reaction that's happening. You're reacting some, drawing, they're diffusing towards the surface, and then you release it, and then there's diffusion away. Something like that. That's the idea, basically. I know diffusion is random. Don't come at me. I know, but that's the idea of it. Whether that's a conversion or an intercalation or anything else, I don't believe that matters. And in fact, the paper that I just showed you was one that I published when I was in grad school. I was using a conversion reaction, and I used a current pulse relaxation technique, which again is very materially similar to GITT. If I'm not mistaken, it's kind of like one GITT segment, whereas with GITT, a lot of times you do it over and over again. You apply a current, open circuit, current, open circuit, current, open, and then the equation is to do some manipulation of the curves to get your diffusion coefficient from that. So no, I do not think it's limited. I think you should be okay to use that kind of technique to get diffusion coefficients.
So while we're talking about Shajil, he has do you want to skip ahead a little bit, because he's got a lot of questions towards the end that have to do with diffusion, and I'm wondering, do we try to address these now, or do we just try to get to other questions? What are your thoughts?
Let's just go top down, because I don't want to
Top down.
focus only on one person just because they're asking a lot of questions.
Yeah.
There's a few other people that did ask stuff. I don't want to skip over everybody.
Yeah. Okay.
Sometimes it's like the same question. We can kind of answer 2 for 1.
Yeah.
But I don't want to, rip anybody off here for the cost of free.
For the cost of free. Okay. So if that's the case, I mean, so we don't know anything about. So I think Abyss.
Yeah.
Abyss Dweller is next. He's asking, what is the difference between a Daniell cell and a voltaic cell? Please explain in detail.
The Daniell cell, right?
Daniell. Oh yeah.
I think it's pronounced Daniell cell. That's
Daniell cell.
That's how I heard it. I don't know.
Yeah. So I think the Daniell cell is, at least just based on kind of Google Wikipedia, it's just the kind of standard copper zinc cell that a lot of people use when they're teaching like general chemistry. And if I just think I can just create one of these, and I don't know how much detail I can go into them, but you have these 2 containers, 2 cells. Oh, I'm gonna make it look a little bit nicer. Yep. Wait, you know what? There.
Don't hit undo.
There we go. Just gotta do that. And then there's solution in both of these. There is a salt bridge between them. So this is a salt bridge. And then I believe one is, so one of these is zinc, and that's zinc. Then the other one is copper. And these two guys are connected. And if I just look up exactly what the solution is, because there's a special solution. So you have zinc and zinc sulfate on one. Yep. So these are both, I think they're both, yes, they're both sulfate salts. So you have zinc sulfate. So this is ZN2+, and you have Cu 2+, and they're in sulfate solutions. So there's a lot of SO4 minus floating around, or 2 minus, I think.
Yeah, 2 minus.
2 minus SO4, 2 minus. And so these are all just kind of floating in solution, and then if this is connected by a wire or a voltmeter, you will measure a cell voltage for this reaction. And I need to look up what those numbers are because I never. Let's see. So it's zinc solid to zinc is a -1. So so that's zinc solid. So we have zinc going to zinc 2+ plus 2 electrons. God. And then you have
all the way off.
All the way off.
Yeah.
And this is at a negative voltage. This is like negative like 0.78, and then volts. And then you have copper. And I think we can draw this. We'll draw this the other way. Copper 2+ plus 2 electrons goes to copper, and that is at I believe that's at a positive voltage, positive 0.34. Is that plus 0.34 volts. And when you hook these up and you have this reaction proceed, you end up having you have to sum these. So I think this one, so the zinc reduction, so you have to flip this around. So zinc reduction is the thermodynamically favorable one. And then in this case, copper oxidation is the thermodynamically favorable one. So I'm going to flip the signs of these for this reaction to occur so that you have positive 0.778 minus 0.34. And that's equal to, what's happening with my, I think it's like offset a little bit. But then when you do that, you get some cell voltage, 0.78 minus 0.34, 0.44 volts. So 0.44 volts. So hopefully you can kind of read
just
it.
The V is under this.
Yeah, just the V is on the other side. But that would be like the cell voltage for this, for a thermodynamically spontaneous reaction. That is what the Daniell cell is. This is one of the, I think, the first batteries that was ever like created or designed or kind of demonstrated, electrochemistry type of stuff. And this is what the Daniell cell is. These are the reactions that are happening. So copper is slowly oxidizing, and then zinc is slowly plating on this electrode, and so you have current passing, charge is balanced with the salt bridge. The one side of the reaction, let's see, this side of the reaction is becoming more positive, so you end up getting a lot more SO4 minus 2 minus coming down on this side of the salt bridge, and you have less SO4 2 minus on this side of the salt bridge. So you have charge balance through the salt bridge, And if you hooked up the device, you know, you'd get some power coming out of it. It's doing some work. There's some charge and current being passed through here. So so there's that. And I believe a voltaic cell is in a way, so this is the Daniell cell, but this is also what you might call a galvanic cell, which means that it's spontaneous in generating current. So it's not like you need an external power source to run this cell to get it to do work. By contrast, if you wanted to run this in, say, reverse, you would need a power supply. You would need, you know, if you want to plate copper 2+ onto the copper and then oxidize the zinc to zinc 2+, you need a power source. Instead of a voltmeter, you would need like a battery to do the opposite reaction. That would be a voltaic cell. So a voltaic, or sometimes called an electrolytic cell, would be the ones where you have to add power into it in order for it to run. But a galvanic, or in this case, a Daniell cell, it spontaneously does the reaction. So hopefully that helps. That's at least a detailed explanation. You know, you asked for a detailed explanation, so I try to give you a
detailed explanation.
A detailed explanation. Oh, maybe I got it wrong. The Daniell cell voltage is 1.1. Yeah, I probably.
Yeah,
I looked at Wikipedia.
I think it's 0.34 minus a minus 0.7.
Oh, minus some. Yeah, that's right. You're right.
Yeah.
Yeah, sorry. It's a minus. Yeah, anode minus cathode.
Look, we promise electrochemistry, not arithmetic.
Yes.
Okay?
Yeah, that's right. Thank you.
One of those is hard. One of them is easy.
Yeah.
I'll let you decide.
Thank you. Thank you for pointing that out.
Yeah.
I apologize.
Yeah. No, you got the right number.
Right
it's just
idea.
It's spontaneous. It's
Spontaneous.
Anyway.
Yeah, it's still spontaneous.
That's correct.
Uh,
This next question, I don't know anything about this, to be honest. What is the chemical composition of quinhydrone? So it looks like it's just a benzene ring with 2 oxygens or hydroxides. But this is what I pulled up from an image search. So it's like that, I guess. I don't know. I guess that's what quinhydrone is. So like this one here, and I guess it's that. I don't know much about it. I'm not sure what's uses in our electrochemistry or as an
a
electrolyte.
type of electrode.
I don't know if it's an electrode. This looks like an organic compound.
Yeah.
If I know anything about chemistry. So you have hydroquinone and quinhydrone and hiquindrone and I don't know. I don't honestly know much about this. Quinhydrone. It looks like it's some sort of
3D
multiple benzene ring, you know, thing of hydroquinone where the like there's almost like bonding of multiple of them. I just don't know enough about it, but that appears to be something like that. That's all that's just what I can pull up very quickly from a search.
Yeah.
I don't really know much more about it. Interesting.
Yeah.
You know, hydroquinone is something I've heard of, and quinones in general, but not quinhydrone. It's like that's different. I don't know. Not sure what it's used for, or what its electrochemistry purposes are. It's interesting, but that's all I can got for you. All right, GITT question. We got that. RCT. Oh, this is interesting. So Shajiel has another question. If the RCT value is decreasing after a stability test of a lithium-ion battery coin cell, what does it mean? Depends which RCT value.
Oh, which RCT value?
Yeah, you didn't say which one. Do you feel maybe if you only have one, I guess. That would be unusual. It's almost suggesting. Well, you did a stability. Okay, so I mean, what is this like a long test? Like if you do a really long, like I don't know, 500 cycles, and the charge transfer resistance is decreasing. Congratulations on your Nobel Peace Prize. I don't know.
Yeah.
You know, you're suggesting a material that's getting better as it cycles. That's getting lower resistance, lower impedance. You know, presumably performing better. Or it's an indication of something else happening, like, you know, maybe that's what the SEI breaking down. Like it's suggesting that a resistance or an impedance, a charge transfer, some resistance is going down over time. So it could be a very bad thing. For instance, if your material is degrading, and maybe electrolyte is ripping apart, or the SEI is thickening, or something like that is happening. That could be a very favorable electrochemical process with a low resistance, but it's obviously bad because the material is breaking down. So that could be one thing about it. Yeah, very generally though, obviously you seem to be on the right mindset, which is like, why would this go down? It should go up. You know, the material should, lose some effectiveness over time, and so its impedance would go up.
This is also assuming that we're assuming that the EIS is done at the same potential or the same state of charge each time.
That too.
So assuming like, oh, it's at the same state of charge, then yes, it's a weird result. He did say that it's after 500 cycles.
Yeah, like I said, assuming at the same conditions for the impedance and same state of charge that your impedance was done before and after, because your RCT will change at 0 or 100% state of charge, for instance. So make sure you didn't do it like at 0 on one end, and then after 500 cycles, you did it at 100% state of charge. Make sure you're doing the same state of charge impedance both times. But I don't know. That's unusual to have a lower. It just, I mean, you might have a material that's performing extremely well. That could be it. I mean, it might could have tremendous longevity, or like I said, it could be an indication of something else is degrading. Surface area or thickness is changing. Maybe.
Could another process be occurring that just so happens to have the same frequency?
Again, that process could be a degradation.
Yeah, exactly.
That's my point. Yeah, you could have some degradation process happening that's appearing to be a really good result. Like, oh, look, I'm getting great. This will happen. Sometimes you'll have like a plateau that lasts forever. Sometimes with certain materials you'll try. It's like, oh, it's charging forever. It's like, no, it's not. It's just ripping the electrolyte apart. This is not charging. This is not going to work. So sometimes it's almost like you got to be careful. The state of charge was different. That's probably actually
okay. Oh, good.
Yeah,
good. Okay.
Make sure those are the same.
Yeah.
Because you will get very different. Like even just before any cycling is done at all, you'll have a tremendous difference in the RCT between 0 and 100%. Because at 100% state of charge, the resistance is very low. It has a lot of energy to give. It's very low. But at 0% state of charge, it's going to have a very high resistance because it doesn't have a lot of energy to give you. You got to put energy into it. So so make sure those are the same. That might clarify it for you. Abyss Dweller says, I wanted to know about quin hydron electrodes. It's also part of electrons like hydrogen and glass. What type of chemicals are used to make? I have no idea. Yeah. I don't know anything about quin hydron. It's the first time I've seen that word. So
yeah. And when you say like glass electrode, like, are you talking about the
like FTO, ITO, or I don't,
or are we talking about shroud materials?
Yeah, I don't.
Like it could be, but I don't know. And then the hydrogen electrode is a different. That's a different thing.
Yeah, there's a lot of words here.
And also, if you're talking about like the standard hydrogen electrode, quin hydron is not part of like the standard or normal hydrogen electrode. It's just like platinum and acid. So, but yeah, I mean, I don't know. I have, this is also the first time similarly I've heard about that. So, but yeah, sorry about that.
So there's a question about a PN junction. It might take me a few minutes to do that one. If I do, there's a quick question that triggers me. What is the point of using a Luggin capillary? There isn't one. I'm just kidding. I hate Luggin capillaries, but that's my own problem. Is it possible to make measurements without it, but just use IR compensation? Yeah. A Luggin capillary's job is to reduce IR compensation in theory. You should just talk.
No, it's
I can't
fine.
say nice things. I can't say nice things
about
so
it.
You should talk.
It's okay.
I have to make snarky comments. So you should talk.
The Luggin capillary, like the point of the Luggin capillary. So first off, just for clarification, I'll try not to take too much time, or maybe I don't know. We end on your favorite thing. But the idea of something like a Luggin capillary is that if you have an electrochemical cell and and then you have like your working electrode is here, solution, and maybe your reference electrode's actually here. But actually, no, I'm not going to put it there. I'm going to put the reference electrode here.
On the next slide. Oh, sorry.
So your reference is here. Let's just say ref is here. Working is here. and then like counters here. So a Luggin capillary is often a tube that just creates a sensing point from the reference electrode to the working, such that it lowers the solution resistance. This becomes like the point. It is as if you put the reference electrode porous frit over here. Like it would be the equivalent if you could move it. So that's why. So that's just to get, what is a Luggin capillary? That's what it is. And the idea is that it minimizes the solution resistance because the sensing point of the reference electrode is placed really, really close to the working electrode. Especially if you have a cell where like, oh, the reference electrode I can't really move it. Even if I moved this over that way, I'd still be like a further distance from the working electrode. So some people use Luggin capillaries to minimize the IR drop. But I think Alex is right. You can use IR compensation to compensate for it. All that being said, like it's good to use IR compensation if you can. IR compensation, in my opinion, should be one of the last things that you do. It's often used a lot, and you can definitely do it. But if you can minimize solution resistance by physically changing the experimental parameters in terms of like the position of the electrodes, or if you add additional supporting electrolyte, it's always best to do that before you go to IR compensation. So that's really the thing. But yeah, I won't comment more.
Better use that Luggin capillary in your half molar solution with your reference electrode in the same vessel. It's really going to matter.
Probably won't matter all that much. You have to have very resistive.
I think that's the reason that I hate it.
What is it?
Because like 90% of people who use it in a situation where it's irrelevant. Like,
you're
using like half molar sulfuric acid, which has tremendous electrical
conductivity,
ionic conductivity.
Yeah.
And it's like you have a electrochemical cell, and the reference electrode is here, and your working electrode's here, and it's like, oh man, I better reduce my IR drop from like 9 ohms to 8.3 ohms by putting a Luggin capillary right over it. Like, what does it matter? Makes no difference at all. Gonna have a school children holding hands of ions from this point here over to here. I hate it.
Yeah. We're kind of a bit out of time.
Yeah. I do see some other questions here. Like there was Abyss asked about a PN junction.
Also,
I actually explained. I did. I
on the last one.
Yeah, I don't know about a diode. It's not.
I
don't know if it's a PN junction diode or like a Schottky junction. Some of that is a little more complex, but I talked in depth about a PN junction and how a solar cell works on our last episode. I think it's 107.
Yeah.
Abyss. So I would encourage you to go back. Probably in the timestamp. I'm guessing I put a timestamp for a PN junction.
I remember it was probably one of the last. It was like one of the last questions of last week.
Yeah. So I did that full explanation. You might be able to check that out. So I just don't have time to go through it again.
Yeah. And Cinnamon Kai, I answered this like exact question
like an hour and a half ago.
At the very, very beginning, Ramna asked the same question about the difference between equivalent series and charge transfer resistance in the EIS. So Cinnamon Kai, that's.
And then Shishil, you asked some questions about the finite and infinite diffusion. So the shortest answer is there's a webinar on this. You can look in our webinars playlist. I have a whole webinar on part of a 5-part impedance series, but one webinar on Warburg, infinite and finite. I describe that with figures, with the mathematics and the plots, how they look. I would explain a little bit now, but we're just running out of time. Just trying to make sure I see your questions, and we're just running out of time here. What's happening at a Warburg? Again, kind of go into a lot of details in a webinar about that, on diffusion and all that kind of stuff. Just trying to make sure make sure everybody knows that. Yeah, we see your questions here. This is our time that we tend to stop, so we're kind of going to have to call it here. Apologies. We appreciate the questions. If you do have more questions, please join us. Are we here next week? I don't actually know. I think we're here next week.
I think we're here next week.
Yeah, we got 1 or 2 more weeks, and then a little bit of a break. I'll be out of here for a couple weeks. But possibly able to join. Anyway,
The last comment, I think we should at least make a comment. We're not currently planning, at least, unless you are,
no,
to attend the AICHE meeting in November. So
no, we haven't historically actually as a company exhibited at AICHE or attended it. I'm from chemical engineering when I was in grad school, and so so that was a meeting that like my group would go to sometimes when we had as these things come, when you have data to present and whatever. But as a company, Pine, we haven't gone to that meeting. So no, you will not find us there. It's
maybe in the future.
It's possible in the future.
Possible in the future.
I've looked into it actually.
Yeah.
And to this point, we haven't gone, but yeah, possibly in the future. We will be at ACS just happened this week.
Yeah.
The Electrochemical Society meeting is in Chicago in October, I believe.
Yes. And I will be there.
Yeah, Alex will be there. I don't have any more US travel, but if you are internationally, I'll be at the ISE meeting in Germany. It's in Mainz, Germany in September. It's in a couple weeks. And then there's a meeting in Italy. It's called Giornata. It's got more Italian words. And then it's like Days of Electrochemistry is the loose translation. In any case, that's like the Italian Electrochemical Society meeting, and that's the week after ISE, and it's in Italy. And I'll be at those two meetings in September. So if you happen to be in Germany or Italy, I'll be at those meetings. And then we have ECS in Chicago, and we go to MRS, Materials Research, which is in Boston.
It's also in Boston.
Our colleague Tim will be there, and that's usually after Thanksgiving. So,
yeah, it's usually after Thanksgiving.
Late November, early December. So that's the rest of our company's travel and trade shows for this year. Abyss Dweller and Shilgila, sorry we didn't get to all of your questions just for time here. Join us next week. We do this at 1 p.m. Eastern U.S. time is when we start. So join us as early as you can. We don't always, unfortunately, we do it thanks to you. We have so many questions, and we appreciate everybody joining us. The downside to getting more people joining us every week is that we just don't always have time to answer everybody's questions. We do our best, but join us earlier, and your questions are more likely to get answered. We do our best to get to those. So I hope everybody has a good weekend and a good week ahead of you. We will see you next week. Until then, take care, everybody.
Have a good one.